Greetings, our scientists. We're going to start the meteorology overview with a look at the composition of the atmosphere, which will play an important role in understanding air masses, air pressure, weather systems, and weather disasters. So really, the atmosphere is an interesting portion of the Earth's surface because it does so much for us. It is simply a mixture of specific gases, with the primary two being nitrogen and oxygen. Nitrogen is 78% and oxygen is 21%. As you noted back in solar systems and astronomy, Earth is unique. One of the reasons why is because it has such a high concentration of oxygen in the atmosphere. To recap the memory of how that happened, two vehicles by which we got so much oxygen in our atmosphere. One was through outgassing of volcanoes back in the Precambrian, and then the most important vehicle was stromatolites, and you've learned about stromatolites and what their function is on Earth. Now, carbon dioxide makes the third most prevalent type of gas that we have in our atmosphere at 0.036%. And then we have argon and a few other trace elements of different types of gases that exist. So when you take a look at all of the proportional volume of gases, you can see that carbon dioxide is a little less than argon, oxygen's number 2, nitrogen comes in number 1. Water vapor is an important component of the atmosphere as well. It makes up about 4% of the total air volume that we have in the atmosphere. It's important because it retains substantial amount of heat. It's a greenhouse gas, and it helps form clouds and it helps produce precipitation, obviously. Interesting fact about water vapor is that it must have something to attach to. You'll learn a little bit more about that later in this unit. Aerosols in particular are dust or particulate matter, and these can be tiny solid or liquid particles in which you can have a condensation nuclei, which means water droplets can attach to that. They're important because one of two things will happen. If they're dark aerosols, they absorb heat. If they are light-colored aerosols, they reflect heat. So that can be important in terms of climate shifts and climate changes. In terms of a daily affair, that's important because at sunrise and sunset, that's what helps give us color in the sky is the condensation nuclei in which water vapor has attached itself to an aerosol. Another component of the atmosphere is ozone. Ozone is O3, and O3 is really important because there's two places that we find it on Earth. The most important place is the one that sits about 30 miles above the Earth's surface. That's called the stratosphere. That's where we have our nice thick layer of ozone, of O3. That's the stuff that shields us from ultraviolet radiation, so we call that good ozone. That'd be a good test question. Good ozone is stratospheric ozone. Bad ozone is that stuff that's right down at the bottom of the atmosphere, which touches the Earth's surface, called the troposphere. Tropospheric ozone is not good because it contains things like volatile organic compounds, NOx gases, which is nitrogen oxide gases, and these can be consumed and breathed in by humans, which can have adverse health effects, not to mention it helps create smog. Now, how long has the ozone hole existed that you hear about? The answer is that it originated in 1979. That's important for you to know. This was the year that the monitoring satellites were launched into polar orbits and we could actually document it. So does that mean that's when we know it came into being? That's when we can prove it came into being. Are there any natural causes that could explain this weird ozone hole that we have in the stratosphere? Well, the answer is yes. In Antarctica, there is a place, Mount Erebus, which is the southernmost volcano that's been active since 1972. Fluorine gases from that volcanic eruption are being emitted and eating through part of the ozone. So there are naturally occurring causes of ozone depletion, not just human-induced anthropogenic causes of greenhouse gases or ozone-eating gases. The structure of the atmosphere is important too because this is the weight of the air mass that actually presses down on Earth. So the heavier it weighs, the more it pushes out the unequal heating capacity of that heat coming off of the ground or the ocean with the atmosphere. So it tends to produce fairer weather conditions. Average sea level pressure is slightly more than 1,000 millibars. You'll get a precise reading a little later in this unit. And it's about 14.7 pounds per square inch. Now, pressure decreases with altitude, and about one half of the atmosphere is located 3.5 miles. I'm doing a very good job of this. So the structure of the atmosphere has to do important. When we're looking at the structure of the atmosphere, we first have to discuss air pressure, because air pressure is the actual weight of an air mass that's pressing down on the Earth. That would be a good test question. An average sea level pressure is around 1,000 millibars. We'll give you a precise number in a little later in this unit. And when you look at that, that's about 14.7 pounds per square inch as that air is pressing down on the Earth. The higher the pressure of the air mass, the more it weighs, the more it pushes out the potential for an unequal heating of the atmosphere, which means you're going to probably have more stable air masses that produce more fair weather conditions. Atmospheric layers are layered according to temperature. The troposphere is the layer that we live in, it's the bottom layer, and the temperature decreases with altitude, called an environmental lapse rate. It is 6.5 degrees centimeters per kilometers on average and 3.5 degrees Fahrenheit for every 1,000 feet on average. That's depending on whether it's wet or it's dry. Thickness varies. The average height is about 8 miles, and the outer boundary at the top of it, which touches the stratosphere, is called the tropopause. So when you're looking at the troposphere, here's the top of Mount Everest to kind of give you flavor. It's about 7 miles up here. 7 or 8-ish miles. Here's the tropopause, and then we get into the stratosphere, and you'll notice this thick layer right here is the ozone. Well, we've got some holes in the ozone, and that's what we're concerned about. So we're going to be learning about all of these parts of the atmosphere right now. The stratosphere sits up to between 12 and 50 kilometers, and in that 12 to 50 kilometers above the Earth's surface is where the most important layer that protects us from ultraviolet radiation exists, and that's the ozone layer. And that's sitting somewhere between 15 and 20 kilometers. The mesosphere sits above the stratosphere and the stratopause right there. The mesosphere sits between 50 and 80 kilometers above the Earth's surface, and the temperature decreases as you go up in altitude. The outer boundary is the mesopause, so every single one, like troposphere, tropopause, stratosphere, stratopause, and then mesosphere, mesopause, and so forth. The thermosphere is the least defined of all of the segments of the Earth's atmosphere. It's just a fraction of the mass of the atmosphere, but gases move very quickly up there. So you're looking at this section of the atmosphere when you're talking about the thermosphere. Also where we have the northern and southern lights, called the aurora borealis. Now, the Earth's motions do affect how the sunlight and air masses move. As the Earth revolves around the sun, it rotates on its axis and it produces seasons. So it changes the angle of the sun. If you've ever noticed, if you have a room in your house that receives sunlight on a regular basis, let's say at 5 o'clock in the afternoon, in the evenings, might be different during the winter and fall months than it is during the spring and the summer months. That changes the total amount of daylight that we have accessible to us. The daily path of the sun in the middle latitudes is in the northern hemisphere, so during December that sunlight actually is lower, closer, and it's lower in the sky than what you would see in the middle of summer. And the relationship of that sun angle also matters, because where you are on the globe determines the angle at which you get direct solar radiation. So the place that you'd expect to get the most direct ultraviolet radiation would be at the equator, the least would be at the poles. So while you may be really cold at the poles, you don't run a higher risk for skin cancer up there, but higher elevations means you're closer to the ultraviolet sunlight. So there's kind of a trade-off. Now, what is solstice versus equinox? These are caused by the Earth's changing orientation to the sun. Our current axis is inclined at 23.5 degrees. The axis is always pointed in the same direction. And there are several days of the year that are special in terms of the Earth's and Sun relationship. One is summer solstice, which is usually either on June 21st or 22nd. And that's when the vertical rays are located directly above the Tropic of Cancer at 23.5 degrees north latitude. So that happens in June, the summer solstice. There's a different date that's important that is also the winter equinox, and that happens in the December timeframe. The amount of water vapor in the air that causes humidity is important because humidity defines when you can start to get precipitation. Saturated air is considered to be saturated when it's filled with water to 100% capacity. Capacity is temperature dependent, and the warmer the air, the more capacity it has to hold water. So when you look at measuring humidity, we talk about relative humidity. That's the ratio of the actual air mass's ability of content compared with the vapor that's actually there for saturation in relationship to the temperature that exists. So that can actually change. Let's say you have a dew point of 60 degrees. There has to be some other information like how much moisture is in the air, how much pressure is there, and the actual temperature that it takes that air mass to reach a 60-degree dew point. So when you hit a dew point, essentially you've hit the 100% saturation rate, and you should experience some form of condensation or precipitation. A couple of things that impact air is orographic lifting. This is when you get like a mountain or some kind of an elevated area geologically that acts as a barrier, and it can create a process like we learned in Death Valley where you get, or you will be learning about Death Valley, where an air mass will go up one side of the mountain, reach its dew point, rain on that side, but never rain on the desert side of the feature. Frontal wedging is when cool air acts as a barrier to warm air, and fronts can create major cyclones that can lead to important weather phenomena. You'll be learning about that in air masses. Convergence also lifts air. That's where the air is flowing together and rising, creating low pressure. And where you get convergence, you should also be seeing stormy weather. Sometimes you'll get localized convective lifting that happens when there's unequal surface heating that causes pockets of air to rise and buoyancy to change, so you can get localized storms as well. Stable and unstable air masses are important to understand as we move into air masses. So stable air has very cool, dense air that tends to sink, and the reason it does this is there's no adiabatic cooling. You'll learn about adiabatic and lapse rates for both dry and wet conditions and air masses, so stay tuned for that. So when you're looking at temperature versus relative humidity, notice that the humidity goes down as the temperature goes up. So your humidity is going to get higher where you're going to have more moisture in the atmosphere. So that's important to understand because there is a direct correlation with humidity and temperature. So the lower the temperature, the higher the relative humidity can be. When we measure relative humidity, we use several ways to do it. There's a psychrometer, which is the most common way and the one that I would want you to know for test purposes. That compares temperature of a wet bulb thermometer and a dry bulb thermometer. There's a second one I'm going to want you to know about that actually uses pressure. We'll look at that in a second. So when an air mass is 100% saturated, it means it has 100% relative humidity. On a psychrometer, both the thermometer and the side-by-side temperature, wet bulb and dry bulb, read the same. The greater the difference between the thermometer readings, the lower the relative humidity will be. When you have absolute instability of an air mass, you're going to have adiabatic cooling, and this is where environmental lapse rate is greater than the dry adiabatic lapse rate. In this particular case, unstable air masses don't sink, they rise, and because of that, they'll make towering thunderclouds like cumulus nimbus. You'll learn about them soon. Conditional instability occurs when the atmosphere is stable for an unsaturated parcel of air, but unstable for a saturated parcel of air. So when we look at unstable air masses, they're the ones that predominantly produce precipitation. And then you get things like cloud droplets, and that's important because not all storm systems will produce rain. But if you get a cloud droplet less than 20 micrometers, that's 0.02 millimeters in diameter, they fall incredibly slow, and that would be a nice, slow, gentle rain if you were to have those kinds of cloud droplets. When we make precipitation, the Bergeron process is the way in which we interpret how the cycles of moisture go through to reach a freezing point. The temperature in the cloud is typically below freezing, and ice crystals collect water vapor, and as they do, large snowflakes will form and fall to the ground or melt during the descent and fall at rain. So looking at this is the Bergeron process. You can see that you'll start somewhere up high in the atmosphere and you'll get ice crystals that form. So essentially every time it rains somewhere up there, it's probably cool enough to produce ice, and it's melting on its descent down. And remember, a condensation nuclei is whatever solids, fine particulate solid matters in the atmosphere for water vapor to condense on. The next thing is the collision and coalescence process. This is where we're going to get warm clouds. Hygroscopic condensation nuclei are out there, so some kind of large material like carbon-based emissions could do that. And this will cause very large rain droplets to form, not very fine ones. So droplets collide with one another, and this is going to be common where you get rain bursts that last for a short period of time but happen frequently, like in the tropical areas. So I will see you next time for air masses. Get ready because you're going to learn a lot of neat stuff in air masses. Take a break and I'll see you back soon. Bye.